so you want to do this basically. Magnitude. Say 3, 4, 5. Okay. And we've got the number of earthquakes. Okay, I'll do this one here. So say you've got, say similar to that, one of your tables is like this: 3,500, 450, 53, 7, 1. Okay. So that's the data you've been given over, say, let's say 70 years. Data, right? Let's see, we're going to. Okay, so you start from the bottom. That's the number. So how many earthquakes over 70 years have exceeded 7? 1. How many, oh sorry, I'll put this here, sorry. 7, 6, 5, 4, 3, 1, right? How many earthquakes have exceeded 6 over 70 years? 8. Sorry, 8? Yeah. How many have exceeded 5? 61. How many have exceeded 4? 511. Right? That plus that. How many have exceeded 3? Sum of all these, right? Okay. So that is. So that's the number of events exceeding 3, 4, 5, 6, and 7. And what's the annual rate? What do I do to get the annual rate? What do I do to get the annual rate? That's over how many years?
7.
So what do you think I do with these numbers? Divide by 7. Okay. And then I can take a log, take the log of that, log of this annual rate. Okay. This is annual rate lambda. Take the log of lambda. Okay. And I'm going to end up with, say, in this case, values about this one. Okay. Then if I plot this against this, on this one here, I'm going to end up with this. I end up with that, and then you can get Excel to come up with a formula for you using regression, and you're going to get something like this in this case. Okay, so that's your Gutenberg-Richter relationship. That should be log. Log. Okay, it's a log then. Log. Okay, so that's okay. Now, what does the question say? The question says you want to come up with. I just bear this in mind. So the question says estimate the Gutenberg-Richter parameters. So the Gutenberg-Richter parameters are actually the A and the B. So but this is in log base 10. This is in the log base 10. Okay, so I've taken log base 10 here. Okay, so just you need to convert this into log base into log normal. So to do that, you multiply this by 2.303. So when you multiply log base 10 by 2.303 for these values, okay, and what you do is you end up in the log normal space. Log normal. Okay, so that and that's A and B. So what we want is alpha and beta. Alpha and beta. This is what we want. Okay. And once you've got that, so that's the first part. So for each of the sources, you need to do this. Estimate the Gutenberg-Richter parameters. So obviously, you need to come up with your relationship. You need to. Then you've got your site source distance distribution. We talked about that. Now, once you've got your Gutenberg-Richter parameters, then you come up with your magnitude probability distributions. Okay. So how do you do that? You doing this. And I've sent you as part of the notes for the assignment. Here's an example here, actually. So in the notes for the assignment, I've got, okay, just hold on a sec. I've got item 2, assignment notes for question 1. Given the following source zone, okay, this is an example on how to calculate your recurrence relationship. But we can also express it using exponentially, so this is how we calculate it, okay? So here's another example in the notes. Okay. Okay, and then probability of exceedance. For each sizing zone, you'll need to consider the following: the site to source probability distribution. We've discussed that, so you need to come up with something like this. And then the magnitude probability distribution. So assuming earthquakes of magnitude less than 4 do not contribute to the seismic hazard, the mean rate of exceedance of magnitude 4 events can be derived from the Gutenberg-Richter relationship. Okay, so remember this value here. Remember in the homework assignment just before I said magnitude, for that particular example, magnitude 4 events happen 1 every 5 years, so the probability is 0.2. Well, in this case, you're going to have to calculate this value here, right? By just from the Gutenberg-Richter relationship, putting in the magnitude of 4, because that's the minimum one that we're going to consider. Okay, and then you've got this value here. So remember in this example here, this threshold annual rate of exceedance of 0.2. You're going to have to calculate that for each of your source zones, right? Which is basically, once you've got your Gutenberg-Richter relationship, just plug in the value for magnitude 4, and you'll get that value here.
Well, what's that value actually mean? Is that the?
It's just that's just the probability of the threshold event occurring. So that's basically if any event occurs on it, what's the probability of that event being one that you have to consider? And you're just using the lowest value of 4 that we're going to consider. So you're taking that probability. Okay.
Yeah. So is that part of the bounded?
Sorry?
So is that doing the bounded?
Yeah, that's bounded. Okay, yeah. So then to calculate your probability of here, so you want to come up with a probability distribution for your magnitudes, and that comes from your Gutenberg-Richter relationship. You want to follow this procedure here. And it's all listed down. We're using this here, this cumulative distribution function. And you're going to come up with that using this formula here. Okay, just follow through. Okay. And then you should be able to calculate your values for this. Right? So that means you've got your now you've got your magnitude distribution, right? The magnitude distribution. You have the magnitude distribution. Okay, and then so you come up with your probability distribution for that. And once you've got your magnitude probability distribution, what's the question? Calculate the probability of or exceedance rate of at least one earthquake. Okay, these questions here pertain to probabilities which you can obtain from the Gutenberg-Richter relationship because they are talking about probabilities with relation to magnitude. Okay? And then you need to plot a seismic hazard curve. And we've talked about how to plot a seismic hazard curve using these target accelerations. And once you've got your seismic hazard curve, then you're going to answer a couple of questions regarding probabilities with your seismic hazard curve. Okay, so that's part 1. Okay? So before we leave today, I'll go over use the Poisson distribution again. Remember the Poisson distribution to calculate probabilities? Let's have a look at that one more time so you know what that is. Okay, so that's part 1, and then you've got part 2. So part 2 of your assignment. So anyway, in the upload to Moodle, you've got these notes here. Okay, and sorry, I didn't realise you had all this. You got these notes on how to do what I've just mentioned. Okay, and then this part 2. So look at part 2. So part 2, okay, these are more worded questions. So I want you to write a few short paragraphs on the response spectrum. What does it mean? Okay, theoretically how it's derived. I want you to talk about deterministic seismic hazard analysis and probabilistic seismic hazard analysis. So you can talk about that. And the exam questions will be similar to this. I just want you to have an understanding of this.
How much do you exercise a short few paragraphs?
Just a few short paragraphs, right? Okay, now this is a little bit of a. Okay, so here, seismic hazard curves are often used to derive uniform hazard spectra. Explain what is a uniform hazard spectrum, and with the aid of illustration, explain how uniform hazard spectra are derived and how they are utilized. So this is a little bit more advanced than that, but I've got some notes in there as well, in that folder. There's some notes on uniform hazard spectra as well. And this actually pertains to how we come up with the response spectrum in the code as well. But just do a little bit of research on that and write what you can. Okay. Then question 3. Elastic site spectra for the New Zealand code have been derived from a probabilistic seismic hazard model. Explain the variance in the spectral shape for different soil types. What implication do these curves have on the potential surface ground motion? So what I'm saying is that in the New Zealand code, you've got your, you've got CT. Yeah. Okay. Remember that when once you multiply all your coefficients, that ends up as an acceleration. Okay. This is a response spectra, and it's like something like that. But you've got different curves here. Okay. Explain what the significance is of these curves. Okay. Question 3.
Where do we get that information? Because I don't think we've got it.
Just have a look. Just have a look at the code.
Yeah.
Have a look at the code and just think about it, and you'll get an understanding. It's pretty. That's a very simple question. Just have a look at the code.
Because whenever I've thought about it, like I don't really understand why. The science behind the reasons why is our next topic, actually. Okay.
But I want you to understand what the implication is. Like.
Right. Yeah.
Yeah. Okay. So you'll see. Have a look at it anyway, and obviously you can ask me questions over the next lecture, and then this is due in the first week after the break, right? Yeah. I don't mind putting it the second week after the break, but it just means my time's compressed with marking as well as I've left it to write at the end, and then I'm trapped because I've got to do all this marking as well as get the exam out, etc. Let's try and I'll think about it, but let's try and keep it the first week, if not maximum the second week, so you get a chance to ask some questions again. But if you start this week, then you're going to be able to ask me some questions next week. Here, just go to the site here and play around. They've got a on the USGS site, they've got a unified hazard tool. And you just follow the questions here to come up with the answers. That's pretty self-explanatory. Now, question 5. You can do a bit of reading here, a bit of research. So in 2010, the National Seismic Hazard Model, like a PSHA, was updated by GNS. Okay, that's the GNS is down in Wellington. They do a lot of our seismic research. Note that the previous model, published in 2002 and used as the hazard basis for the New Zealand loading standards, was based on a PSHA model which incorporated 305 seismic sources, okay, and attenuation expressions for earthquakes modified from overseas models to better fit New Zealand. So the new model, based on a national scale update of the fault sources and distributed models, okay. A new model was based on a national scale update, okay. And just gives you a bit of background into the two models. So with reference to the above in your own research, I want you to just come up with some answers here. You can provide the seismic hazard maps for both the 2002 and 2012 models and answer some of these questions. Between the two models, where is the location with the most apparent increase in hazard? Where is the location with the most apparent decrease in hazard? You can print out the response spectra for these locations and describe the difference in the models. So that sort of is a summary of basically PSHA in New Zealand, and hopefully this is something you're going to understand where basically the basis of the New Zealand code for earthquake hazard. Okay. Actually, most of this stuff, look, if you start Googling this stuff here, the answer is going to come up pretty quickly in the research papers, a couple of research papers, and you can read them and get that information. Okay. And then the last question is a very simple question in terms of estimating. We talked about triangulation. So if you get the, if you've got the relationship between the P wave and the S wave, I remember that when an event occurs, the P wave's the faster wave. So that arrives at the size of the ground first. And if you get the time difference between the P wave, the arrival of the P wave and the S wave, you can use that to triangulate where the earthquake is, okay? So to triangulate, you need a minimum of 3, okay? Data from 3 points. So essentially all you need to do is apply this equation here for this, with this data here, and you can come up with the location of where the event happens, okay? So that's just to give you an idea of triangulation. So that's assignment 1. Okay. So most of the work is in that part 1, and this stuff here is a little bit of research. All right. Just to round off this in the next, maybe we have a 10-minute break, and then we'll just have a recap on Poisson's distribution, through those questions, and then I think that then you'll find for assignment 1, get started as soon as possible, so you can ask me questions. And yeah, okay, so let's have a break. Make sure you're back by 7:10.